Okay, so a 2.5 kilogram object is initially moving north at 5 meters per second. If it's brought to a stop in 0.5 seconds, what's the impulse? All right, so the way I think that I would start off with these questions, guys, is as soon as you get this, it's kind of just picking out what it is that you need from these equations. You've only got really one formula for this. I'd write it down to kind of get my bearings. So write down force is equal to change in time, or sorry, force times change in time is equal to mass times change in velocity. And then I remind myself that this is the impulse, right? Or J, right? You could call it J if you like. And this is my change in momentum. So just, that's the theory part. I just need to kind of get those things separate. Just, they actually are equal to each other, but when they ask for one, it technically is impulse is force times time. Now, this one, mass times velocity, that's your change in momentum. So triangle momentum, triangle P. All right, so now what are we looking for? So it says, what's the impulse? All right, so I can actually use either of those because they're equivalent to each other, right? So I'm just trying to figure out, just piece this together. So I've got a mass, and I got a velocity, and it says brought to a stop, though, right? Because remember, this velocity isn't like just one velocity. That's actually like, there's actually two velocities hidden in there, right? That one really means VF minus VI. But we're gonna get off lucky here because if it's brought to a stop, one's gonna be zero anyway. But so we can put this in. So let's say we'll write this out. It'll be impulse, or J, is equal to mass times VF minus VI, right? That was just mass times velocity from the first one. Okay, and then this will be, what was it, 2.5 kilograms times, and then VF, like you said, was 0 minus 5 meters per second. So we get an impulse of negative 12.5, and then the units for impulse? Yeah, or Newton's time seconds, right, not per. So Newton's time seconds, or kilograms times meters per second. They're actually equivalent. They actually break down into the same units anyway. So say that's your impulse, right? Now the second part, so we got that one. Now it says, what's the force required? Okay, so the force required, what do you guys think here? Looking back at this equation, can we do that now pretty easily?
Yeah, can we just move change in T over?
Right, exactly, because we just found this, right? We just found that. That was our impulse, or change in momentum. If I want to find my force, right, I just need to divide both sides by T, that change in time, right? So we'll just say the force is equal to, I'll just write it right in now, negative 12.5 kilograms times meters per second divided by a time of 0.75 seconds. So we get a force of negative 16.7 newtons. Alright, just a couple things I just want to kind of highlight here. Our impulse was negative 12.5. Let's just make sure that that makes sense with the negative, right? So it was moving north, right? So this thing was moving north, and then it's brought to a stop. So our impulse was negative. That actually means that in this case, right, if our object was moving north, the impulse was the other direction, which actually makes sense. That's the way it's going to work, right? The impulse would be like almost like a resisting force pushing you back, right? So that's kind of what you're looking for. And if you would have just called 5 meters per second your V there, right? You would have got a positive number of that because we ended up going 0 minus 5 to get that negative in that one, right? So it is important to make sure that you write it out like that, right? To get the negative, because one of your answers on multiple choice would have had positive 12.5, right? So just careful on that. And then again, this one makes sense too, right? That the force ended up being negative, right? Because that's the force really of like the friction on me, right? It's the friction on the tires pushing back on the car. So from the car going north, there must be a force pushing back on me to make it come to a stop. So that negative makes sense, right? All right, next one. Okay, so on this one too, I'm going to talk a little bit about some of the theory behind impulse too. So a 75 kilogram person falls from a height of 2 meters. If the person lands on a bed, what is the change in momentum? What is the impulse? The stopping time was 0.75 seconds. What average force did the bed apply on the person? Okay, so just in general, before we do this one, let's talk a little bit about impulse and like cars and seat belts and airbags and everything else. Because here, we got. Can you guys write this down? Force times change in time is equal to mass times change in velocity. And let's actually just focus on this one for a second. So I'll say J is equal to force times change in time. All right, so if I'm looking at this one, my what can happen here in any collision, right? Any collision would end up having the same impulse, right? So if let's say I'm in a car or this person hitting a bed or whatever, right? If I'm in a car and I collide with, let's say, a wall, well, what's going to happen? There's a certain amount of impulse that happens there, right? There's a change in momentum. I had some momentum, and then I didn't have any momentum, right? I went from a car moving fast to a car not moving at all. So there's a change in momentum. So that change in momentum is like a fixed number, right? Let's call it, just so you guys can kind of get an idea here, let's call it 10, just so we have a number, right? Now, if I want to keep that number the same, can you guys kind of see that if I made my force bigger, right, what would have to happen to the time to make it work out the same? It would get smaller, right? So big force would equal small time. And doesn't that make sense, right? If you were in a car and you smash into the wall, if it happened instantly, like within like a fraction of a second, that's a big force being applied on you, right? If the other was true, right? So if I went the other way and said so J is equal to force times change in time, and we had a very big time, what's going to happen to your force? That's going to have to be a very small force, right? Which of these two situations would you rather be in?
Less force.
That one, right? That's the idea. So when people are designing like airbags or cars or anything else, right? They're really keeping this in mind, right? Because the force, that's the one that kills you, right? That the force is a bad one, right? That's the one that's going to be the one that's going to make you yeah.
Time eventually.
Yeah, time's gonna kill you too.
Yeah. Sure. Yeah. Okay.
Both need to catch up.
I like that. So how do manufacturers of cars, let's say, how do they increase the time, right? Because that's their goal. They want to increase that collision time. What do they do?
It would inflate instantly and then kind of deflate, so that.
So like an airbag you're talking about?
Yeah.
Yeah. So when you hit the airbag, right? Why is the airbag better than the dash? Right. That's pretty much what it boils down to. Why is hitting the airbag better than hitting the dash of the car?
Because it feel like direct resistance over cyclical time.
Yeah, that's what it is. They're just increasing the time that impact happens, right? So the airbag, right? It's a cushion. That collision lasts longer. It's like slightly longer, but it's enough that it saves your life, right? Because the dash, you actually will embed into the dash a little bit too if you're going fast enough. But that impact is very fast, right? And that's very very small time equals very very large force, and that's what kills you, right? So this all kind of makes sense. Like if you're bungee jumping, right? Would bungee jumping with like a rope work?
Your leg goes to
Yeah, like bungee jumping with a rope would be a bad idea. we we use a bungee cord to bungee jump, right? Because we're just really increasing the time that happens, right? That's the whole deal there. So there's a lot, like in this course, there's a lot of like theory type of questions where they talk about this in general, right? So how do you save someone's life? Well, it's always about increasing the amount of time so you can decrease the force. But if you aren't trying to save people and you're trying to like, let's say you're a pile driver, right? And you wanna like, you guys know what piles are? Yeah, like you smash your pipe or whatever into the ground for like a pile. If I want to maximize that, well, what I want to do is like minimize my time, right? I want to have a small time so that I have a big force so that I can like maximize the amount of force that happens in that collision. So there's situations where you want either one. Yeah.
So how does seatbelt impact?
Same thing actually. Seatbelt, even though you wouldn't think a seatbelt has any give, it actually does have some give. It like you actually do like the seatbelt flexes a little bit, and it definitely flexes more than the dash does. Right? And there's other reasons too. Is that like if you don't have a seatbelt, you might go through the window and then you're getting cut and everything else too, right? So there's advantages to you just staying in the car. The other one that cars do, right, is when they do their collision test, what they do is they make the whole front crumple, right? So they design them so that they wreck, but they'll wreck like in a safe way. And yeah. So what they do is when let's say the front of the car crushes inward, they're actually pretty clever about it too, where they'll make it crush inward and crush like under you. So like the car when it crumples, it'll crumple and like underneath you, so you're kind of sitting there hopefully safe, right? Where it's not crumpling into you, it's crumpling under you. But it's all with the idea of maximizing time. That's really the idea when they're doing these car collisions.
How would they make the front crumple zone into a giant 1,000-pound piece of metal over front?
What's that? Well, because metal, they make it crumple, right? That's why old cars are made. Yeah, old cars are made of like pretty rigid steel, right? And they weren't safe for that reason, where you'd smash into something. And even though there's a big front, like it's long up front, it's made of pretty hard steel. It's not giving, so even if I hit a wall with that car and it's not giving, that's still going to be like an instant stop, which is what ends up killing you, right? So now the thing is, like the smart cars, right? They don't really have a front end. So I don't know. I hear they're pretty. They've done some cool engineering to make it again so it like crumples underneath and stuff, but.
But they're
I
all
don't know.
Yeah. Okay, so let's do this question now, with that in mind. So a 75-kilogram person falls from a height of 2 meters. A person lands on the bed. So here, we've actually done kind of questions like this in Physics 20. So we've got a person. Okay, so person. There's their legs and their arms. They're falling down under the bed. So that's before, and let's say right before they hit the bed, I'm going to draw another person. And let's say this is bed now, right? Is this dotted line? So what's going to happen here? The actual, like when it says the impulse, right? I'm concerned about this, right? Because what's going to happen is this person is going to sink into the bed. Right? So they're going to hit the bed and they're going to sink into the bed. That's the collision. So that's when you're thinking impulse, you're like focused on the collision part of this, right? Not the falling part of this. But the whole thing is we actually need the falling part of this because we got to figure out how fast they're going. We don't really know that bit of information to begin with, right? So what I might do is like again, if it was me and I didn't know how to get started on this, again I'd write down my formula. I'd be like, okay, so force times change in time. Is equal to mass times change in velocity. And it says, what's the impulse? All right, so I'm looking through here. I've got a mass. I got a time, right? So I got a mass. I got a time. Yeah, I don't have enough info here, right? I either need a velocity, right? What's that? V equals d over t. No. Okay. Anyone know why we can't use V? Well, and like so, right now, I want the velocity right here, right? I want that velocity right before they just sink into the bed. When something's falling, why can't I use this equation? It's accelerating, right? So I can't use that one. So, good try though. Yeah. We actually could. There's actually two ways. Remember, we could think in kinematics or we could think in energy.
Yeah, let's take potential energy.
We can use potential energy in this case, right? And that'll be good because it's less to do actually. So let's do that one first so we can figure out our velocity right there, right? So we'll go, shouldn't have wrote that right there. Sorry guys. Let's go EP, right? Because it's all potential energy up here, right? And that's all kinetic energy right before you hit the bed. So we're going to say EP is equal to EK. And then we're going to fill it in. So EP is mgh, and EK is 1/2 mv squared. Which is nice because now I don't even have to put mass in, right? I can rearrange for this. We end up getting 2gh. The square root of that is equal to v. So then v is equal to the square root of, what would that be? 2 times 9.81 times 2 meters.
39.
Equals, and then square root, right? So 6.26 meters per second. Okay. Put a box around that because we need that. All right, so now that's part one of our question, right? Now we're actually gonna, because that's how fast I'm going right here, right? How fast am I going right there? Right at the bottom, right when you sink in, right? To the bottom of the sinking into the bed. Right, that's where you stop, right? So the collision is that eventually you're gonna come to a stop. You would spring back up again, but really we're just talking about the collision of hitting the bed. So you're gonna come to a stop right at the bottom there, so that's gonna be V0. So right now, I've got, you know, V1, or VI, whatever, is equal to this number, 6.26 meters per second, and my V2 is equal to 0. So we actually have all the info we need now, right? Because we can use our equation, change in, or force, times change in time is equal to mass times change in velocity. And it says, what's the impulse? Okay, well, I'm going to solve this part. Yeah? Oh, sorry, what's the change in momentum I wanted first? Yeah, so we'll go, okay, so change in momentum is equal to mass times change in velocity. So your change in momentum is equal to 75 kilograms times, and now this would be what? Yeah, negative or 0 minus the, yeah, 6.26 meters per second, just VF minus VI. So that ends up being, oh, sorry, 0, we made a mistake here. Something right here. Should be negative, right? So we took the square root of it. Remember, it still makes sense in math because whenever you take the square root of the number, it's actually a positive or a negative, right? There's both. It's up to us to know that actually this was the negative version of it because it's going down, right? So like we knew at this point right before you hit the mattress that they're actually going down. So this really would have been negative. So then when in our equation when we put it in, right, this would have been 0 minus negative 6.26 meters per second, which minus the negative would really be positive, right? So in the end, our change in momentum is going to be, yeah, positive 469.8 kilograms times meters per second. And check if that makes sense, right? The change in momentum would be the other direction, right? So if I'm falling down, the change in momentum would be up. So that does make sense. And then the next part says, what's the impulse? So the impulse, or J, is going to be the same number. Positive 469.8. I'm going to write it more in terms of impulse and call it newtons times seconds, right? Right, just newtons times seconds. And then the last part if stopping time was that, so you guys, we've done this before already too, right? So if I want to find the force in like this equation, let's say, right? I've already just found that one. I've really just got to divide by t. Right, they just gave us the time there. So we'll say force is equal to our number there. 469.8 newtons per second over our time of 0.75 seconds. So our force is 626.4 newtons. Okay, that's it.